So today we're looking at section 7.3. We will be spending a couple days on this one. It says multivariate linear systems and row operations. Basically what we're doing is we are looking at solving systems that have more than two variables. And we're going to incorporate some of what we did in 7.1 with the substitution and elimination methods. But we're also going to look at how could we use a matrix to help us solve these larger the larger systems. So for today, we want to solve systems using different methods. For example, we want to look at how could we get them in a triangular form, and what does that mean? We're going to look at a process called Gaussian elimination. We're going to look at elementary row operations and how we get something into row echelon form. And then we're going to use our calculators to take it a little further into reduced row echelon form. Okay, so that's as far as we're hoping to get today. And then tomorrow we'll look at how we use an inverse matrix to solve a system and applying it to some real world examples. Okay. All right, couple terms. It says methods for solving linear systems or first degree systems, meaning we're not going to deal with quadratic ones. Okay, we're just dealing with linear ones. The methods that we had for two variables can be employed to solve equations with more than two variables. The goal of the elimination method, is to rewrite the system as an equivalent system of equations whose solution is obvious. So we're going to do the same stuff that we did in 7.1 with our elimination method. We're going to try to get rid of some variables. And basically, with each step, we're taking that system and we're rewriting it as an equivalent one. But we're going to keep rewriting it until we get it down to something that we can solve. All right? And as long as we use appropriate steps, our final system will have the same solutions as our original. Okay? A triangular form of a system is an equivalent form from which the solution is easy to read. Triangular form allows us to solve the system using substitution. We are going to refer to it as back substitution. Okay. Now, we're not going to actually solve this first one because it's used again in example 2. We'll solve it there. But I just wanted you to see what we mean when we say triangular form. It's called that because the left side of this equation or the system kind of looks like a triangle. Your bottom equation just has one z in it. Your middle equation has two variables, a y and a z, and your top equation has an x, y, and z. Okay, so it's kind of looking like a triangle. If we can get it into this form, we can do that back substitution method. So when I look at this, what do you notice about the bottom equation? It's a single variable. It says z equals 3. I already know what z is, right? So triangular form is something that makes it easy to look at our solution. We know the first number. We know that z is 3. And then we can simply do some substituting back in. If I know that z is 3, can I plug that in for z in my second equation and figure out y? And then if I know z and y, can I plug those into the top equation and figure out x? Okay, that's why it's called back substitution. We're working our way back up the system. Okay? All right, so let's see how we can use that. So the idea of getting it into triangular form is called Gaussian elimination. So it's that same elimination process that we used with two variable systems, but it's named after Carl Friedrich Gauss, who came up with this plan. The things that we are allowed to do to convert our system into this triangular form. we are allowed to interchange two rows. So maybe your top row has just a plain z in it, nothing else. Well, we can move that to the bottom. Okay, so we can interchange two equations. We can multiply or divide an equation by a non-zero real number. So we could take equation 1 and just double everything, right? Times everything by 2. We can do that and add it to another equation. Okay, so we can add two equations together. We could multiply by a non-zero constant and then add them together. We can interchange two rows. All right, so those are the steps I'm allowed to do. Now, the process. Every system is going to be a little different, but that your steps are all going to be with the same goal in mind. And that is, the first thing you have to do is eliminate the x's in equations 2 and 3. I don't care if you get rid of the x's in equation 3 before you get rid of the x's in equation 2, but they both have to be gone before we move to doing anything with the y. Okay? If we are trying to get this in that triangular form, we don't want this x here, we don't want this x here, and we don't want this y here, right? Eventually, we want all of those to be gone, so we just have a 1x in the top, a 1y in the middle, and a 1z in the bottom. Okay? But we have to get rid of those two x pieces in equations 2 and 3 before we move to getting rid of this y in equation 3. Okay? You have to do it that way. If you try to get rid of, say, the y first, when you go to try to get rid of the x's, it's going to come back. Okay? So there's a process. We want to get these two terms, that 3x and that 2x, to become zeros. Then we can work with these more basic equations to get rid of our y's. Okay? And it'll make more sense as we go through this. So my first step, let's say I'm going to get rid of the 3x here. What would I have to do to the first equation to be able to combine it with the second one and get rid of my 3x? Multiply by, if I multiply this by -3 and added it, would that cancel out the x's here? So think of that elimination method that we used in previous math classes and we reviewed in 7.1. If I times this top equation by -3, when I add the top two equations, the x's would drop out. Does that make sense? Yes? Okay. What's different is you have to be very clear which equation you are changing. We are not going to be adding equations 1 and 2 together and creating a separate new equation. We still want equation 1 in there. So when we go to do this, the notation that I want you to write is that we are going to take row 1, okay, or equation 1 if you want to say that. We're going to multiply it by -3, and we're going to add it to equation 2. I'll call it row 2. Now, what we are really trying to change is row 2. I'm using row 1 to make that change, but I'm not eliminating row 1. It's still going to be there. Okay? So my new system, my row 1 is still going to be there. So I'm going to write that one down. My row 3, I am not doing anything to. So I'm going to write row 3 down. What I'm trying to change is row 2. So what you're going to do is you're going to do this multiplication and addition in your head and just write down your new row 2. Okay? So if I take -3 times this x, I get -3x. Add it to the 3x underneath, I have 0 x's, right? No x's. If I take -3 times the -2y, that makes 6y. If I add it to the -5y, I get 1y. If I take -3 times z, add it to the 1z underneath, I get negative 2z. And if I take negative 3 times the 7, it makes negative 21. I add it to 14 and I get 7. Sorry, negative 7. Are we good with what I just did? So I just was changing equation 2, but I was using equation 1 to do it. Okay? Now, my next goal would be to get rid of this 2x here. Okay? I can do that same process. I can use equation 1. I can multiply it by what? Negative 2, and then when I add it to equation 3, the x's will go away. Yes? Okay. So we are going to take row 1. We're going to times it by negative 2. We're going to add it to row 3. Okay? So my new system, I am not changing row 1. I'm not changing row 2. I just want to change row 3. So we're going to take row 1. We're going to times this row by negative 2, right? And add it to row 3. Negative 2 times x plus 2x, it's gone. Negative 2 times 2y would be 4y. Added to the 2y at the bottom gives me 2y. Negative 2 times the z, it's negative 2z. Added with the bottom negative z gives me negative 3z. And negative 2 times 7 gives me negative 14. Added with 3 is negative 11. Have I made the x's look the way they're supposed to look, where there's a single x in the top and none in the other two equations? Yes? Okay. Now I can move on and I can try to get the y's to be the way I want them. And that is to have a single y here, which I do, but to have no y's here. Okay? Now, I don't want to use equation 1 anymore, because if I multiply equation 1 by something and add it to equation 3, I'm going to reintroduce x's, and I don't want to do that. So if I'm trying to eliminate this 2y, I need to use an equation that doesn't have x's, that's just dealing with the y's and z's to combine with the y's and z's in my bottom equation. Does that make sense? So what can I do to row 2 and then be able to add it to row 3 and get those y's to drop out in row 3? Multiply it by negative 2. Good. Okay, so we're going to multiply row 2 by negative 2 and then add it to row 3. My first equation doesn't change. Second equation doesn't change. I'm changing my third one. Okay, so negative 2 times this row gives me negative 2y plus the 2y. Y's are gone. It gives me positive 4z combined with negative 3z would be 1z. Negative 7 times negative 2 is 14. Combine it with negative 11, and we get 3. We have just taken our original system and converted it into an equivalent system in triangular form. This is what we had in example 1. This was the system we were looking at. So our bottom equation tells me that z equals 3. Okay? My second equation, I can now back substitute that in. So if I know that y minus 2 times z equals negative 7, I can dump in that 3 that I found to be equivalent to z. And what do I get for y? And now that I know z is 3 and y is -1, can I back substitute it into the top equation and figure out x? Okay. So I have x minus 2 times -1 plus 3 equals 7. So x plus 5 is 7. X would have to be 2. So my solution is the ordered triple. X is 2, y is -1, z is 3. Okay. Questions? Couple comments. In triangular form, we solved this system. It had one solution. The leading term of each equation had a coefficient of 1. We had 1x. That's not what I meant to do. We had 1x, we had 1y, we had 1z, right? That's your goal when you have a triangular form. You want those leading coefficients just to be 1. The third equation only had the variable z. The second equation had a y and a z. The third equation, the top equation, had a x, y, and z. Okay? So that's what you're trying to make it look like. All right. Let's try it on this system. What can we do to start getting rid of the x's in equations 2 and 3? Let's start with equation 2. What could we do to get rid of the x's in equation 2? What can we do? Could we just add equations 1 and 2 together? Right? Wouldn't the x's drop out? Okay, which equation are we changing? We're changing equation 2. Okay, so we are going to add row 1 with row 2. We are changing row 2. All right, so my new system, row 1 does not change. Row 3 doesn't change. I'm changing row 2. So picture adding rows 1 and 2 together. What do we get? We get no x's, we get a negative y, and we get negative 4z, and constant 7. Okay. Next step, let's get rid of the x's in row 3. What could we do to get rid of those 5 x's? Okay, so we're going to take row 1 times negative 5. We're going to add it to row 3, and we're changing row 3. All right, first equation doesn't change. Second equation hasn't changed. Third equation. If I take negative 5 times this top row and add it to the bottom row, what do I get? X's are gone. We get 15y plus a negative 13y. So 2y. We get negative 5z added with 13z. So 8 z's. And we get a negative 20 added with an 8. Okay. All right, what's my next step? What, Carter? Okay, so we now want to combine rows 2 and 3 somehow, right, to get rid of the y's in row 3. So if we multiply row 2 by 2 and add it to row 3, would that work? Yes? No? Okay, first row didn't change. Second row we haven't changed. Third row, when we times the middle row by 2 and add it, the y's drop out. We get negative 8z's plus z, so we have 0 z's. And we get 14 with a negative 12 is 2. Now here's where we run into a problem. What happened in the bottom equation? All our variables disappeared. Okay? Think back to when we solved a system. If all the variables disappeared on the one side, you had to look at what was left. Is it a true statement or not? Can 0 times z equal 2? No. 0 times anything is going to be 0, right? So in this last line here, we're getting a false statement. 0 times z cannot be 2. We say there's no solution to this system. Okay? Now, I do want to point out one other step. Let's say the z's hadn't disappeared, we still had some left. Okay? What would we have to do to equation 2 to get it in the form we want it? We need to get rid of the negative in front of the y, right? We want it to just be a 1y. Top equation should start with a 1x. Middle equation should start with a 1y. Bottom equation should start with 1z. So could we multiply the middle equation by negative 1? Just change all our signs on that one? Okay. So if the z's had still been in there, that would have been my next step. Okay. All right. Now, we would like a faster way of doing that, or a shorthand way of doing it. And that is where we shift to a matrix format. Instead of writing the x, y's, and z's every time we rewrite that system, we can create a matrix that doesn't have all the variables in it. But the way we're going to set up our matrix is going to indicate to everybody else what that equation really was. It's kind of like how we use place value. If I write the number 214, we know that means there's 2 hundreds, and there's 110, and there's 4 ones, right? Because we know the place value system. When we set up a matrix, and we want to get rid of our x, y's, and z's, we have to all be consistent. So your first column in your matrix is going to represent the coefficients of your x's. Your middle column would be your y's. Your last column will contain the z's. Does that make sense? And then if we make it into an augmented matrix, then we get a column of our constants as well. So when we look at this first system, it's actually the one that we used back in example 2. It's the same system. We start out with a system of equations. We can take the x, y's, and z's out and create what's called a coefficient matrix. So if you look at this, you've got 1x, 3x's, 2x's. Your first column is 1, 3, 2. Okay? The coefficients of your x's. Your second column is your coefficient of your y's. Your third column would be your z terms. Does that make sense? So sometimes we want just a coefficient matrix, and we're going to use that tomorrow when we start working with inverses to solve. For today, we actually want what's called an augmented matrix. And that's where we add in an extra column here that comes from these constants in our system. So we basically have all of our x's in the first column, our y's in the second, our z's in the third, and our constants in the fourth. Okay? And then we can manipulate the numbers, and we don't constantly have to be writing all the x, y's, and z's in there. Okay? It just looks a little cleaner. All right? So if I were going to take this augmented matrix here and try to solve it and put it in what we call that triangular form, where we get zeros here, here, and here, and we create a diagonal of ones, okay? My first step, if I want to eliminate this 3, could I times the top one by negative 1 and add it to this one? Yes? It's the same thing we did in example 2. It's just we took the x, y's, and z's out. Okay? So your steps here are the steps we've already done. But we did them with a system of equations in example 2. Here we're going to write what would the augmented matrix look like. Okay? So I know we've already solved this one. We're going to go through quickly. We said we're going to multiply row 1 by -3 and add it to row 2. And it created this system right here when we did that step. If we weren't looking at the systems and we were just looking at the augmented matrix, timesing the top by -3 and adding it creates a 0 here. Timesing the top by -3 makes a 6, adding it gets me a 1. Timesing the top 1 here by -3 and adding it gets me -2. Timesing the top by -3 makes -21, adding gets me -7. And that is my row 2. I have no x's, I have 1 y, I have -2 z's, and my constant's -7. Okay? The other equations didn't change. Okay? Then if we were trying to eliminate this 2 here, we would times the top one by -2 and add it. So -2 times the top equation plus the bottom equation gets me a 0 here. -2 times my top equation makes a 4. Added with the -2 gets me a 2. -2 times the top one added gets me a -3. -2 times 7 is -14. Adding to 3 is -11. And that's my bottom equation. And again, we didn't change the other 2. Okay? So it's just showing you that we can do the same thing with a matrix as we did with a system of equations. So what's my bottom equation going to look like, or my bottom matrix? Top row would be 1. Okay, middle one? Bottom? Okay. You can back substitute once you've got it into this form. We called this triangular form, right? Because we had nothing in the bottom corner, it looked like a triangle. This, there, you'll notice there's a number everywhere, right? Every space has a number. But the bottom little chunk are all zeros. This is called row echelon form. Okay? This is triangular form over here. When we actually have a system of equations with the x, y's, and z's in there. When we switch it to an augmented matrix, we just call it row echelon form. Okay? You will be expected to solve a matrix like this, to get it into row echelon form, and then be able to back substitute from there. Okay? By hand. So our goal is to take a system of equations, write the corresponding augmented matrix, and transform it into row echelon form. From there, we can use back substitution to get our solutions. Okay, so couple definitions. Row echelon form. If you have a row that consists of all zeros, like we had in that, no, we didn't have one yet. If you have a row that's all zeros, you want to move it to the bottom. Okay. The first entry in any row that doesn't just have zeros has to be a 1. So that leading coefficient has to be a 1. A 1x, a 1y, a 1z. Okay. the bottom line here really just means that those ones are moving to the right as you move down your matrix. Okay? So we're trying to get a 1 here, a 1 here, a 1 here, right? And these are zeros. Okay, so that's the goal of row echelon form. You'll notice that these elementary row operations are the same exact things we said you could do with a system. You can interchange two rows. You can multiply a row by a non-zero constant. You can add two rows together. Okay? All right. The one thing I'm going to caution you on, you must show me what you're doing each step of the way. You have to put that notation down, 3 times row 1 plus row 2, whatever it is that you're doing. If you bring a question up to me, or you have your test and there's a mistake and you haven't written down what it is you were trying to do each step, I'm not going to try to figure it out. Because there are options. There's different routes you can take to get to the same thing. Okay? Some of you might eliminate the x's in row 2 first and then go to row 3. Some of you might choose to get rid of the row 3 ones first and then do row 2. There's things that you can do where it's slightly different order. I'm not going to try to guess what it was you were doing. Okay? So you have to have the steps listed there. So our first step is going to take this and write it as an augmented matrix. In other words, get all the x, y's, and z's out of there. Okay? So my top row, I have 1x, I have a negative 1y, I have 2 z's, and a constant of negative 3. Okay? My second row would be 2, 1, negative 1, 0. What's my third row going to be? Okay, I heard negative 1, 2, negative 3, 7. Yes? Okay. So going with that, and I should mention that some textbooks will put a dotted line here before the column of constants, kind of like where the equal signs would have been, just so you can see where are my x, y's, and z's, my variables, where are my constant pieces. Some books do it, some books don't. It's your choice. If it helps make it clearer for you, you certainly can use it. Okay? All right, so our goal is to make this become a 0, this become a 0, and that to become a 0, right? Those bottom 3 sections. Let's start with the first column, right? We want to get the first column correct before we move to getting the second column correct. What can we do? We could times the top row by negative 2 and add it to row 2. Agree? Okay. What do we get if we do that? Remember, our top row doesn't change. What we're really trying to change is row 2. So I'm going to bring over my other 2 rows since I'm not changing those. Okay. Take negative 2 times the top row of numbers and then add them to the middle row of numbers. So negative 2 times 1 plus 2, 0. Negative 2 times negative 1 makes 2. Added to the 1 makes 3. Negative 2 times 2 is negative 4. Adding it gets me a negative 5. Negative 2 times negative 3 is 6. Adding it to 0 is 6. We good? All right. What's our next step? Add rows 1 and 3. Okay. We are changing row 3, correct? All right. So row 1 doesn't change, and row 2 doesn't change. All right. So what's my new row 3 going to look like? Do my x's go away? Okay. Adding the negative 1 and the 2 makes 1y. Adding the 2 and the negative 3 gets me negative 1. Adding negative 3 and 7 gets me a 4. We good with that? Okay, now, a couple options. I eliminated the x in row 2, but I want it to start with a 1y, and right now I have a 3y, right? So one option would be to say, I'm just going to times everything by 1/3. All right, I'm allowed to do that. However, it would make the z term here negative 5/3, which means we're dealing with fractions. So if there's another option, I would use it, right? If you can get by without having to create fractions, that's better. So remember that we can interchange 2 rows. So what if I took my row 3 and swapped it with row 2? Then would it be right? I'd have a single y as my first piece in that one. Okay, so my next step here is I'm just going to flip-flop rows 2 and 3. All right, now my row 1 looks good and my row 2 looks good. I just need to get row 3 to not have those not have those y's. What could I do? Do what? Yeah, you do not ever want to go back and use row 1 now. Because remember, if I start multiplying row 1 by something and adding it, I've reintroduced my x's. So at this point, once I've got the zeros for my other x's, I just want to work with rows 2 and 3 and combine these somehow to get rid of these y's in the bottom. So we're going to take, what did we say, row 2 times the negative 3 and add it to row 3, and we're changing row 3. Good with that process? All right. Rows 1 and 2 haven't changed. I'm changing row 3. I still have no x's. When I times row 2 by negative 3 and add it to row 3, I get no y's. Timesing negative 1 by negative 3 makes positive 3. Adding it to negative 5 gives me negative 2. Timesing the 4 by negative 3 makes negative 12. Adding it with 6 makes negative 6. And we're almost there. What do I do now? I need to somehow get this bottom row to start with a 1 instead of a negative 2. Can I times everything by negative 1/2 and get that to cancel out? So I'm going to take negative 1/2 times row 3, and then I'm not going to add it to anything else. I'm just going to adjust row 3. Put it up here. Okay. So I end up with 0, 0, 1, 3. All right. I'm going to put that dotted line in again so you can see. What does the bottom equation tell me? It tells me z equals 3, right? This was 1z equaling a 3. So I have my first variable. What does my second one tell me? Just give me the equation. 1y minus 1z has to equal 4. Yes? Okay, so now let's back substitute. Let's put that 3 in there. So y minus 3 has to equal 4. Y would have to be 7. All right. Taking my top equation, it says 1x minus 1y plus 2z's has to equal -3. And we know a y and a z now, so we can substitute. Our y was 7. Our z is 3. So we have x minus 7 plus 6 would be -1. X would have to be -2. So my solution, x is -2, y is 7, and z is 3. Okay? All right, now, what you see in this slide, we just did all of this. Okay? All of these steps you see above the blue line were what we just did. We got it into row echelon form, where you have a diagonal of 1s here, and these are all zeros underneath. Okay? If we had continued those steps, and we now tried to get zeros here, my board's off a little bit here. We then are putting it into what's called reduced row echelon. And if you take it all the way to that step, you don't have to back substitute. Your bottom equation says z equals 3. Your middle equation says you have 1y equaling a 7. Your top equation says you have 1x equaling a -2. So some people don't stop at row echelon form. They just keep going with those row operations, and they keep doing things to convert it into this reduced row echelon form. We are not going to expect you to do that. As soon as you get it into row echelon form and back substitute, we can do it that way. Okay? But do know that you could continue these steps. Once you've got the bottom zeros, you could get this to be a 0, and then you could work on column 3, getting those to be zeros. Okay? It's an option. We're going to use your calculator to take it all the way to this RREF format. So grab your calculators. We're going to create an augmented matrix for our original system. In other words, make this into a matrix by just getting rid of your x, y's, and z pieces and just leaving the coefficients in there. Okay? So I'm going to pause the video here. You guys go ahead and enter that as a matrix A. Okay, so you've entered this as matrix A. We are going to go back into our matrix screen now. And this time I want you to arrow over to the math option. And then you need to scroll down a ways. Do you see the REF? Choice A. And then choice B is our REF. So if you use REF, you're going to have to back substitute. If you use our REF, it takes us those few steps further, and there's no back substituting needed. Okay? So we're going to go RREF. So select that one. Then tell it what matrix you stored it in. I put it in matrix A. And hit enter. All right, and those are the same answers we got in our last example, right? So from this, we know that x has to be -2, y has to be 7, and z has to be 3. You're getting your answers right from that last column. Okay? Again, we would still write it as an ordered triple for our final answer. Okay? We're going to do one more really fast. Go ahead and write the augmented matrix for this matrix, or for this system. What do you notice? Okay, so our first row, We have a 1x, right? And the columns under it are zeros, so that looks right. My second row, the first thing is a 1y, and there's a 0 underneath it. That looks right. But what happens here? I have no z's left, right? I didn't just get rid of the x's and y's in that bottom equation. I also got rid of the z's. And so look at the statement that you have left. Can 0z equal 0? Yes. In our previous example, we had 0z equaling 2. We said that's not going to work. But 0 times any number z will get you 0 for an answer. So this is a case where we have an infinite number of solutions. And how we write our answer, we go back and look at what is this first equation telling me? It tells me that x plus 3z's has to equal 5. Yes? And if I solve that for x, I'd have to move my negative 3z's to the other side. Okay? So now I have x being an expression that involves some z's. Okay? Look at your second equation. We had 1y, what is that? Minus 2z equaling negative 2. Well, if I solve that for y, I could add the 2z over and get an expression for y that just uses z's. And so when I go to write my final answer, my x expression is negative 3z plus 5. My y expression is 2z minus 2. And we're saying that z could be anything, because 0 times anything gets you 0 for this bottom equation. Okay? So you're going to encounter one of these in your homework tonight. Try it. We'll do a few more of that tomorrow as well. Okay? On the homework slide here, you will notice that some of them say to do with a calculator. Some of them are saying to do those row operations by hand. So you might want to take a picture